and I'll hand it over to Paula, who will introduce our speaker and program for today.
Okay, well, thank you, Julianne, and good afternoon, everyone, and welcome to space. Our speaker today is Dr. Norman Fitz-Coy, who is an associate professor in the Department of Mechanical and Aerospace Engineering in the Wertheim College of Engineering at UF. And he will be speaking to us today on an issue that has developed over many decades as we've placed more and more satellites into Earth's orbit, and that is the categorization, monitoring, and management of space debris, or more familiarly, space junk. Dr. Fitz-Coy first moved to the US from Jamaica at the age of 19 to study engineering at Auburn University, where he received his Ph.D. in aerospace engineering. His areas of expertise include dynamics and control of multi-body systems, orbital dynamics, flight mechanics, vehicle health management, and game theory. His current activities include deployment dynamics for satellites and spacecraft, autonomous rendezvous and docking, ground vehicle dynamics, cooperative control for formation flight, and system health monitoring. In 2018, Dr. Fitz-Coy was funded by NASA and the Air Force for a 5-year, $3 million project to characterize the debris fragments from 2 laboratory hypervelocity impact experiments, which will generate important data required to improve existing spacecraft breakup models used in the assessment and prediction of the orbital debris environment, and give us a better picture of the space debris that could potentially jeopardize other satellites. Studying the way materials break apart due to space collisions gives us the ability to accurately predict the amounts of orbital debris in low Earth orbit, which is critical for space traffic management, and will also help us to minimize future impacts from space debris. So with that, I'd like to welcome Dr. Fitz-Coy, whose talk today is Space Debris. Was the movie Gravity correct, or Hollywood hyperbole? Welcome, Dr. Fitz-Coy.
Thank you, Paula and Julie. Thanks. So, yeah, I wanted to talk a little bit about some activities that I've been doing here. Actually, the award that Paula spoke of was the second of the 2 NASA awards. The first one was actually building the satellite and doing the hypervelocity impact. And that started in 2000, I believe, in 12. So we've been working at this for almost a decade now. We built the asset, which I'll show in just a minute, and then we are in the process of characterizing the fragments that we've gathered from that. In hindsight, just as an FYI, in hindsight, if I knew this was what I was getting into, wouldn't do it. It is a tedious task to do the things. It's enjoyable, but gosh, it's tedious. Okay, so here's the NASA movie, the space debris movie. And let me just see if I can play this clip here real quickly for you.
Explorer, this is Houston.
Go ahead, Houston.
Mission abort. Repeat. Mission abort.
Explorer, this
So I believe you've seen this.
Contact with debris. Debris
Some
is
of
from
the
a
things
VSE
here
Repeat.
are somewhat true, but
We have to go. We have to go. Go.
a
Go.
lot of it
Meteorological conditions.
really Hollywood's
Explorer, Dr.
glorification
Stone requesting
of
faster
the
transport to
process.
Bay Area.
There
Explorer,
is
you
an
copy.
issue with
Explorer,
other
permission to
things,
retrieve Dr. Stone.
the Tesla problem, which the movie here is trying to exploit. But in fact, I don't think they did an
Look,
excellent
we need to get the hell
job.
out of here. Need some help there, man? No, don't wait for us.
This issue is basically stating
Man
that
down.
we will get to a
Man
point
down.
that it becomes self-sustaining. Debris will generate more debris, which will generate more debris, and we will have at the moment, we're not close to that. We do have
Astronaut
to do
is
some
off
action.
structure. Dr. Stone is off structure. Dr. Stone, detach. Must detach.
I think I'll stop that and get back to the real issue here. So the bottom line in this is that, you know, yes, to some extent, the movie was portraying things that are of interest to us, but the majority of it was, the hyperbole of Hollywood. This is a set of charts that it's dated 2010, and it's something of what Paula had shown earlier. And it's showing the different images of the Earth on the left. In each image on the left is an image of just the Earth itself, and on the right is a further image which goes out to show us the geocentric orbits that are there. Okay, so this is 1957. We're going down 1970. We're starting to put more stuff out, but we're also starting to put stuff out close to the geo orbits. And so that's why this image here is showing you things out in the geo orbits. And you can see that we're populating by 1980, we're populating more things, and the same thing is happening out in the geo. And by the time we get to 2010, which is over a decade old now, we can see quite a bit of population in Leo, very close to the Earth, and then we see quite a bit of population out in the geo orbits. And these things are indeed problematic for us, okay? There are potentials for losses due to collisions and things like that. In fact, we have had a collision of a satellite with essentially a piece of debris, and I'll talk a bit about that. As I stated in Paula's thing, is that the size of the element shown here is not to scale, so then don't be alarmed by how thick it is around the close proximity, the Leo orbits around Earth. There's just a lot of stuff there, but quite a bit of it under about 600 kilometers, let's say 500 kilometers. Most of that stuff will eventually come back down. Once we get up to 800 and above, it stays there for much longer time, and that's where the problem starts. And the same thing is happening out here at the geo orbits. And what happens in the geo orbit is that there's a bit of debris. Well, once the satellites have exhausted their usefulness, they're typically put in a graveyard orbit, which is higher than the Leo orbit. What we have found is that it appears that stuff is leaking off of those, or stuff is leaving those satellites, and the smaller they are, the more they're affected by solar radiation, and therefore their orbits change, and they do come back down and cross into the geo orbits. So that is something that is of interest currently, and it's something that we're looking to resolve ASAP. It's not been resolved yet, but we're looking to do that. So just a bit of information about the types of debris we're talking about and the things that are significant. The things that we can see from the Earth is a baseball and larger. So it's this size element, 10 centimeters and greater. If we look at that, we're in the 25,000 or so type elements, type fragments. If we go down a bit smaller to a 1 centimeter, we're about 500,000. And then if we go down to 1 millimeter, we're over 100 million fragments. And so the issue really comes from the 100 million fragments. Now, what we have found, and I'll show you shortly, is that we do have quite a bit of this much smaller stuff here, not necessarily the 1 millimeter, but the 2 millimeters and greater. That actually comes from a fragmentation of a spacecraft. So this is indeed something that we need to be aware of and be concerned with. The fact is also, if we're above, the 800 or so kilometers altitude, they don't fall back to the Earth rather quickly. So they're there for quite some time. And this is what we're getting a lot of this stuff from the ASAT missions that have been, ASAT is anti-satellite, where, you know, you shoot down the satellites. This image here is just to show that a paint chip of a size of 0.2 millimeters, a paint chip provided this size damage on the Challenger's window. So the fact is these things are really dangerous. And the reason for that is the speeds at which they're traveling. They're traveling, you know, in the order of about 10 kilometers per second in Leo. So we have to be careful of those things. So just a bit of background as to what's happened there. In 1996, there was a operational French satellite that was affected by debris. The one that stands out the most is in 2009, and I'll show you some results on the next slide here. An Iridium satellite, which is an operational satellite, was hit by a Russian retired satellite, the Cosmos 2251, and that generated quite a bit of debris. And this was not an ASAT. It was not something that was planned. It was just these two objects in orbit, and you know, the Cosmos collided with Iridium. We also have had, from the space station, the space shuttle program days, quite a bit of interest in MMOD. I forget that I need to be careful. Micrometeoroid or orbital debris impact. Okay, and so those items, whether they're micrometeoroids, which means that they're not human generated, or orbital debris, which is human generated, do constitute quite a bit of stuff in space, and there's quite a bit of collision that's happening with these things. And so at ISS altitude, you know, there was quite a bit of collisions or potential collisions. So again, these things need to be taken into consideration. The big ASAT that most everybody talks about is this 2014 ASAT by the Chinese. Now, in all retrospect, the US has done ASAT missions, Russia has done ASAT missions, China has done ASAT mission, and India has done ASAT missions. Those are the four countries that have had demonstrated ASAT missions. However, others do have the capability. They just haven't demonstrated the ability to do it. And I wish they wouldn't, because it is not necessary, okay? The other thing here is that because of these debris fragments in space and the potential for collisions, satellite operators have to be on the lookout for these warnings and, you know, make a decision whether or not to maneuver their satellites out of the path of the debris. So you will get a warning from Celestrak, and you would take that and you would propagate your orbit several times and go through the minutiae of the details there to make sure that you won't have an impact, or if you have a potential impact, that you are in an ability to avoid such collisions. And so these are things that happens on a daily basis. And the other thing here is that there's a lot of satellite anomalies that we don't know what they are, and quite a bit of it is attributable to untracked debris that's having collisions with antennas or collisions with solar arrays or something of the sorts that are causing these anomalies. So this is an image of the Cosmos Iridium debris field, and this is 7 days after we have the collision, And as you can see, as we move out 7 to 30 to 6 months to a year, the collision spreads, or the debris field spreads over the Earth. Okay, and so these are things that we have to be concerned about, because at the impact, these fragments will go in all different directions. And once that starts, their velocities will be different. And so that's what's generating these different fields that we're seeing here. NASA over the years have done some studies, and this is one of the results that they have put together over the years that's showing that you're seeing things that are, this is the 2007 Chinese ASAT, this is the 2009 Iridium Cosmos, and you can see that the number of fragments there just are changing drastically from these events, okay? And so the bottom line is ASAT is not a good thing to do. It generates a lot of debris, and so we have to then monitor those debris fields. This is one of the NASA generated charts that motivated the DebriSat work that we're doing. And you can look at this, and in this case, you get a model of, this is NASA's predictions. This is looking at the area to mass ratio versus the number of satellites and looking at the different elements. But you can see that the NASA model doesn't accurately predict the iridium fragments that came out. It's okay, but it's not great. In fact, if I had the Cosmos, the two charts would actually almost overlay. They were much better at predicting that. And the reason for that is that these data, these plots that are generated here, the models that were used were closer to the Cosmos satellite than they are to the Iridium satellite. Now, this chart here is, again, a NASA prediction, the blue line, of the debris that showed up from the Chinese ASAT, and you can see that it's not even close, okay? And so here, these two things were the motivation for what NASA wanted to do, which is to improve these models. And in order to improve these models, they needed additional data. What they did not have is data from the materials that are currently in use in satellites, MLI, CFRP, carbon fiber reinforced composites, and titanium, and those sorts of things are not as predominant in the initial models, and hence the reasons why they're doing such poor predictions here. So we were charged with coming up with a model that NASA could do a test on. And let me be clear here, this test is not done in space. This test is a ground-based test, but it would generate the types of fragments that we would expect. So what we had to do there is to develop the model and then take that model to a test facility where they do these hypervelocity impact tests. And I'll show some of those results in just a second. So the takeaway, which is what I said here, is that the NASA breakup models were not good in predicting what the current status is of these satellites. So the DebriSat project was started in the 2012 timeframe, and it was sponsored by the NASA's Orbital Debris Program Office. At the time, it was the Air Force SMC, the Air Force Space and Missile Systems Command Center in LA. Both of those two companies, agencies, I should say, not companies, agencies, sponsored the project. As we know, during the last last presidential era, we changed, and now the SMC is known as SSC for the Space Systems Command, and they're It's the same organization, they just have a different name. The Aerospace Corporation was also involved, and of course, UF. What came out of that is a 56 kilogram satellite that is representative of the types of satellites that you would see in a LEO orbit. And by that, what I mean is it would have multi-layer insulation, MLI. It would have composite structures. It would have titanium elements and those sorts of things. So we built this satellite to be representative of what is currently in a LEO orbit. It is not a LEO specific satellite, because what we had to do was look at the different things that were on these satellites and ensure that we had all of those components on this 56 kilogram satellites. So it's not a functioning satellite that we built, but we went through the process of building it using all the functional components and using the processes that would generate a satellite that could go to orbit, with the exception that we did not have any onboard avionics to work. We were not interested in that because that has nothing to do with the debris that is generated. This satellite we took up to Tennessee, and there is a HVI facility in Tennessee that we took it to, and that's where we did the test. It was impacted with almost the size of a Coke can, hollow cylinder, and that cylinder was going at, we wanted 7 kilometers per second, which would be a low orbital speed. We got to 6.8 kilometers per second, and trust me, we're very happy that we could get that high. So this is DebriSat here. You can see the solar panels here, which are represented by composite materials and 6 cells, composite cells. And you can see different components on the bottom of the satellite here. This is an optical instrument. These are antennas for communications. This is a different antenna for communications. I don't recall what this one was at this time. But the way this thing was built is that the subsystems had different colors, so that once the fragmentation took place, we could relate some of the colors of the items to where we think they came from. Well, I'll talk a little bit about that. That was not quite successful as we thought it would have been, but I'll talk about that. This is DebriSat, this same satellite in its stowed configuration, and the solar panels. So this would be the state in which it would be deployed. And the solar panels are on the backside. You can see them there. This is a picture of a publicly available picture of the test chamber. The chamber is actually on the backside of this wall, and the canister that was shot down at the thing was loaded here and fired along this HVI tube here down into the chamber. This is DebriSat sitting in the chamber, and the chamber was lined with these foam panels. They had done some tests before and did not fully align the chamber. And what happened was that as the fragments broke from here, they impacted the walls of the chamber and changed their shape. And so the idea here is to use these foam panels to capture the fragments as they go radially outwards and downstream. So there you can notice also there's a back wall there. And this is an image of what actually happened. So this is the test article coming towards DebriSat. These are images that were taken during the process. Getting closer, the impact has taken place. The impact is, and by the way, this is all just from kinetic energy. There are no explosives anywhere in it. This is a cylinder with a composite shell around it, hitting the satellite that's stationary. And so you can see the impact again, and then everything was gone. On this here, I believe I have an image that I can show. You'll see the image. Here is the fragment coming in. That's the impact. And there goes DebriSat. And so what we have after that is, this is what the chamber looked like when we were done. You can see the fragments on the floor, bits and pieces of fragments. This here was a star tracker base. And you can see that we were all there up in Tennessee, collecting and sorting through these fragments so we could take them back to UF. We had 21 pallets of boxes, and the pallets were roughly 2 meters by 2 meters by 2 meters in height. And those were shipped back to UF. And we have been, since they have been shipped back to UF, we have been working frantically in trying to get these things sorted, extracted, and then processed. At the time of this impact, the idea was that we would extract 2 millimeters and greater fragments. And the model that NASA had predicted that there would be roughly 85,000 of these fragments. Remember that number. I'll talk about that in just a second. So these are some samples of the fragments that came out. You can see there are some wire elements here. This is a piece of CFRP. I don't recall what that is. This is a piece of MLI, a piece of tubing here. This is a solar panel that's fractured. This is another solar panel. This is MLI. So you can see the different fragments that we were getting out of this thing. So then the idea then was to bring this back to UF, collect the fragments, so then we would have this data set that we could use this data set to improve the existing models. Remember now, we started in 2012. The test was done in 2014, and we have been extracting fragments since 2014. That's why I said if I knew what I was getting into, I wouldn't do it again. So these are the sorts of things that we have been doing since 2014. Granted that in 2020 and 21, during the pandemic, we were really struggling to get anything done because of the proximity people had to work in. So at that time, the idea was that we had recalled that the fragments get embedded into these foam panels. So we had to X-ray the foam panels to see where the fragments are, excavate the fragments from those foam panels, and then get into the characterization of the fragments. The things that NASA was interested in, I should say the things that the government agencies, because both NASA and SSC are interested in, the material, the shape of it, and the color. And the color primarily is two reasons. One is to identify where in the satellite it came from, and two is to get an idea of how much dust was collected on the fragment as it went through the process. We also needed to measure the mass and the size of the fragment. And the size, the thing that they were interested in is basically the average cross-sectional area, which is, if I take the object and I rotate it and took a projection of the cross-sectional area, as I rotated it through 4 pi, I would get an average of all possible areas that would be there, and that's what is called the average cross-sectional area. The other item is the characteristic length, which is the average of the 3 largest dimensions of the fragment. think about that for a second. The three largest dimensions of the fragment, only one of those would be a real measurement. The other two will be projections, and you can't physically measure them with a caliper. So that dictated that we had to come up with some other metric to get the characteristic length. And I'll talk about that in just a second. We also wanted to characterize them as 2D and 3D because that allowed us to do two different sort of size measurements in the process of doing that. And I'll talk a bit about that in just a second. And then we also had to make sure that the equipment we had and the processes we had were performing properly. So we came up with what's known as the gauge repeatability and reproducibility test, the gauge R&R test. And we've been conducting those to make sure that we're doing everything correctly over this time frame. Bear in mind that this is done with primarily undergraduate students, and so at most we have undergraduate students consistently, a undergraduate student consistently for roughly 2 years. So over this time frame, you can think of the number of undergraduate students that have gone through. We've used graduate students to do the technical work, but the actual extraction of the fragments and the characterization of the fragments, those sorts of tasks are typically done by the undergraduate students. So this is the breakdown. So we do detection. Once you've detected where they are, you identify the locations, then you would do an extraction, and then you would get into the assessment where you do material shape, 2D, 3D color. You'd measure the mass, you'd measure the size, and from those you get the characteristic length, the average cross-sectional area, and the volume, and then you do the gauge R&R. And every year, of course, we have an annual report we have to do for NASA. So in order to get the fragments embedded in the foam, what we had initially was an X-ray chamber here on campus. And so in this X-ray chamber, what we did was, this was the receiving end of the imager. So you can see it's rather small, and in fact it was roughly the size of a sheet of paper. The size of the foam panels is roughly 2 by 4, so they're much bigger. So what we've decided to do was to basically take multiple images here and then stitch the images together and figure out where the fragments were. That worked for a while, and we did quite a bit of fragments that way, but eventually this chamber had some issues and we had to move on. And so what we got then is that NASA went and got a TSA X-ray scanner, one that was retired from the airports. And that is the scanner now that we're using. So essentially there's an X-ray imager inside here, and we feed the panels through here, and they come out the other side, and we take multiple images and do all sorts of things with it. But the bottom line is that with that, we can get, in addition to the fragment locations, we can also start now to do some imaging of those things to get the size and shape of it, because I should back up and say this was all 2D imaging. This process here that we're doing here is actually multi-phased imaging, so we can put things together to make it appear as if it's a 3D image. So we can now get size and shape out of these images here. And this is an early version of it just to show the scanner. So now when I go to the airport, I'm excited to see these scanners. The assessment, as I stated earlier, we had to do material, shape, color, size, and those things using a microscope, because some of these fragments were really small. 2 millimeters and above is what we initially started out with. 2 years ago, we went to 10 millimeters and above because it was just taking too long to go down to the 2 millimeter size. And what we found also is that the 2 millimeters that we have now, they're all roughly CFRP. Again, those are the carbon fiber reinforced polymers. And so we don't need any more information on that. Okay, so we decided to go to 10 millimeters and above. We have 15 categories of materials. The next page I'll show you. We have 6 categories for the shape and the, you have flat panels, curved panels, flat rods, curved rods, and so on. And we had 13 categories, all colors for the colors. And I don't remember all 13 of them off the top of my head. I could go look it up, but it's not that critical. The bottom line is that all of that information is on this chart here, and the kids use this in order to do the verification, the assessment of the fragments, okay? Once the fragments are assessed, they're actually put in a database that we actually created a database to do all the handling of these fragments. Just some more images of the fragments. We got some MLI here. This is multi-materials. This is MLI and also CFRP fractured there. This is a piece of aluminum that was initially blue and got damaged. This is a piece of a wire that you can see the wire there, and the sheathing that covers the wire is fractured on the wire itself. And this is a PCB board, a typical board you'd have on the computer. So all these things were there. And this is another 3D element. This is actually a part of a battery box for the spacecraft. Here are the materials that we had. So you had aluminum, CFRP, copper, epoxy, glass, and you can run down the list. And this is an old chart here. I really just needed this list here to show you. This is an old chart that showed the different bits and pieces. This was back when we were at 86,000 pieces. So this was 4 or 5 years ago. So 5 years ago, we were at 86,000 pieces, and that's what NASA said we would get. The model said we would get, and we hadn't even gone through a third of the amount of fragments that we had. So part of what has happened over the years is that as we go through this, I should also point out that everything that we've done here, there isn't anything that started out before us, okay? This is all new, so we're learning as we're going along. So one of the reasons that we went to a 2D and 3D is that some of the fragments were really small, and so we thought that we could do 2D measurements on them. So you put them on a glass sheet, and you take a top image of it, and you estimate the height. And we estimated the height based on a ring that was here. It turns out that over the years, we've developed better mechanisms. And as you can see here, we can actually get the height. There's a fragment here, by the way. We can actually get the height by taking a 45-degree image. And this is what this shows. Come on, this is what this shows. So these are the top images, and this is the 45-degree image that shows the actual height. So we do measure the size of the fragment, and then this is the fragment, by the way. So this is the size of the fragment, this is its thickness, and this here is this ring. We have the ring here as a standard to always use to do the comparisons to make sure that we're getting the right images and right calculations of the dimensions of these quantities. It turns out that 3 millimeters is the limit as to what we could do with the 2D imagers. And so at some point in time, I don't recall the exact date, we changed over to a image, this is the standard image again, that was 3 millimeters in height. The reason for that is we had students who were putting things that were a little bit larger than 3 millimeters on board. And so this eliminated that. If you put it here and the object is taller than this, take it off. And so that was the objective here. We're not critical of the height of this thing. We just want it to be a reference as to how high your fragment needs to be. And this has turned out to be really, really productive for us. So that's one of the improvements we had for the 2D images. The 3D images, I just realized I don't have an image of either of these things. The 3D imager is essentially 6 cameras along an arc, and beneath those cameras there is a rotary table that you take 6 pictures, you rotate 6 more pictures, and so on. And from that, if this is the object, this is a top view of the object, and this is the table that it actually sits on. And we go through that process. We rotate it 20 times. We actually rotate it 21 times. And the reason for the 21st is to make sure that the first and the last corresponded. The first and 21st corresponded. If not, we knew that the fragment moved. And so that was done to ensure that the fragments weren't moving while we were doing this. And so with that, and some processing that we developed also, we could get an image of this, which is what is constructed here. So this is to represent this object here. This is version 4 of it, and it is a little rough, you can see. And this is now the version that we're using, version 4.1, and you can see it is a little better in extracting this information. The things that we're looking for is the X length, which is the measurable greatest length. The Y length is, an orthogonal direction to that, and then the Z length is orthogonal to the XY plane, but it's not a physically measurable length. So I have to come in, and the code that we developed actually goes through that and sorts through all of that and gets those calculations for you. And what you see here are measurements of those quantities. So this is X, Y, Z, LC as the average of those things, and the volume, and the ACSA is the average cross-sectional area. So all of these things are calculated by code that we wrote in order to do these things. And you can see that there has been some improvements in the quantities that we get here. And so this version 4.1 is what we're currently using to do that. One of the reasons why we went to 4.1 is this fragment here, where this is the actual fragment. These are 2 images of the fragment. And these are the reproduced, captured images that we regenerated. And if you notice here, this fragment doesn't have this cutout, and it doesn't have this area here also. And so this made us think, in addition, this, you could see this area here is not properly captured either. And so it made us think that we're getting more in the volume calculations that we're doing and so on. So we went back, and this is the reason why we went from version 4 to version 4.1. And you can see that this object here is much closer to this object, both in these 2 stances. And in fact, when the students are going through this, they have to ensure that they're very comfortable with it. If not, they have to reject it and make a statement as to why it's rejected. So, a couple more slides and I'll be done. So some of the results that we have to date is, remember, we are looking at 85,000. We're at 225,000 and we're not finished yet. We expect we will probably get about 250,000 pieces out of this, okay? So what this chart here is showing the items that we have collected and the items that we have actually entered into the database. So each item that is collected is given its own ID and is entered into the database, and all of the information, the color, the shape, the size, the characteristic length, the average cross-section area, the volume, the mass, all of those things are entered into the database along with that. And so that's what the brown column here shows. Those things are in the database. The green column here shows the things that we have identified and extracted, but haven't actually completed all the items on it. And so this is a model of the mass that we have calculated so far, or not calculated, but measured so far. The blue is representative of the 3D fragments. And so we can see that there's a lot of heavy 3D stuff. And the orange is representative of the 2D fragments. If I were to plot these things versus numbers, this is a very small number here. So of the 225,000, this is probably 10. And the rest of this up here is what's in the 2D fragment areas, okay? So we have quite a bit of 2D fragments, not very massive because they're 2D, but they're still quite a bit. And as I stated earlier, a 0.2 millimeter fragment did a damage on a shuttle window. So again, you know, the fragments are indeed significant. This is just, and this is a wrap up here, this is just the statement of the space traffic management policy. And it says space situational awareness, which is SSA. It's a buzzword everybody in the space industry uses now. Shall mean the knowledge and characteristic of the space objects and those sorts of things, and know whether or not they're stable, unstable, sustainable, and so on and so forth. And space traffic management is the issue in dealing with the coordination and sustainability of all those things. And the point here is that in previous space traffic management, this item was not in there, space debris. Now space debris is in this in the space traffic management policy. Okay, and so it just shows how significant that is. I will send these slides over, and if you're interested, I can send you a copy of this paper. But this is, you know, a paper during the time when we were doing the hypervelocity impact that was talking about, and this is about the time that the time that India did their ASAT mission. They were talking about, in essence, that space debris is a bigger problem to satellites than the ASAT mission. And of course, they're just justifying their statement. But guess what? The ASAT mission generated space debris. And so that's the issue that we have with these ASAT missions, is that they generate a significant amount of space debris. And if you recall the chart that I showed earlier with the Cosmos Iridium and with the Chinese, you can see a huge jump in those space debris fragments. The big thing that is problematic for everyone right now is these mega constellations that are coming. SpaceX is actually moving quite well with their Space Link. Don't know if you heard recently, they had some issues with 30 odd satellites that were damaged by space weather. The satellites went up, and you know, we had some space weather activities going on, and the space weather took them out. So now they are essentially objects up there, but they're not functioning satellites anymore. So they are indeed debris. So that's one of the issues that comes to the forefront of these items, of these things here. And this is my last slide, and I apologize for the time, but this is my last slide here. You know, it's just a comment that I saw this in 2009. I wasn't doing space debris work at that time, but I saw it and I just thought, ah, this is pretty nice. And here I am working on space debris. So thanks for your time. I hope I gave you some information that was helpful. And if you have questions, I'd be happy to answer them.
Well, thank you so much, Dr. Fitz-Coy. That was really fascinating. And I see what you mean by the tedious nature of what you have to do here. And I guess what a perfect job for undergraduates. I guess it gives them all a little appreciation about the nature of research, and it's not all cures for cancer. Sometimes we have to get our hands dirty and do the tedious work. But I have quite a few questions, but so let me just ask the first one and then I'll turn it over to the floor. So I guess the obvious question would be, are there any efforts at cleanup? I know we can expect, as you mentioned, a lot of debris in orbits at less than 500 kilometers are eventually going to decay into Earth. atmosphere. But in the meantime, it seems like we're outpacing ourselves in terms of generating new debris. So I'm wondering if there are any giant like solar net projects, that some, smart person has planned for trying to collect some of this debris.
The answer is yes. There are several activities that are ongoing, but the technology for doing it, I think, is there. We are in a fairly good position to do it. The issue becomes a legal issue, because if, let's say, I had a satellite up there and someone from India wanted to go retrieve that satellite, it could only have one part that's functioning. But if someone from India grabs it, I'm going to claim that my satellite was functioning, and therefore they are retrieving a functional vehicle, and so all heck breaks loose. Okay, so there is that aspect that we have to get through at the moment. The technologist side, there are some issues there, because you have to think also that, this net that you're thinking about, if I wrap this net around the satellite and the satellite has MLI on the outside, that net is going to destroy some of that MLI, and that MLI becomes debris. So I have to be, careful of how we do these things. The things that NASA and ESA are proposing is there are lots of upper stages that are still there, and those are essentially, they have rocket nozzles, and so you can go and fire a harpoon in the exhaust vent of the rocket nozzle and retrieve them that way. So we're looking at doing some of those things.
Oh, fascinating. Okay. Yes, Richard Petway, you had a question?
Okay, I have a kind of ignorant question, but that's the way I am about your topic. And I guess the issue was, I remember that the Russians some years ago had a disabled satellite, and they wanted to use it for practice of missile between satellites, and blew it up. And what happened was the space debris increased, if I think I am correct. So it's really not possible to use satellites between satellites to extract these things, especially a small one, the smallest. But the net idea, it sounds, how would you get something that is so small and then be able to gather it and then to herd them to some particular place by folding down the net? I just find that impossible. So is there realistic ways that we can collect this debris efficiently, or is it to a stage now that we just have to live with it?
So the net idea is not for the smaller fragments. The net idea is for upper stages and that sort of things, full-fledged satellites. The satellites, for example, that the Starlink satellites that were lost recently, those could also be brought down by nets, okay? The smaller debris, quite frankly, there are lots of ideas out there, but no one has a real good idea. So if you were to take, for example, a large foam, and I use the word foam loosely here, by the way, a large foam panel and just push it through space, what you'll do is some debris will attach to it as you go along, okay? The real issue and why they're focusing on the larger fragments is if you minimize the amount of damage that you get with a collision, as we did with Iridium and Cosmos, if you minimize those collisions, then you don't generate as much debris as is possible. The other thing is that there are now things that are put in place that once you launch a satellite, you have to be planning also in its end stages how to get it back home. We can't enforce that because there are no laws that requires you to enforce it, but to be a strong partner in this thing, you kind of go along with those ideas. So the bottom line is that the nets are not for the smaller fragments. We really don't have any ways of dealing with the smaller fragments because it just is impractical to think about it. Because as I said, if you were to go with the foam, it doesn't matter. You go with a foam as big as a football field, that's just a dot in space. So you still aren't going to be collecting as much things as you think you would be. Does that make sense?
Follow-up question, please.
Yeah.
I just thought about the liability of the damage to satellites that a small paint chip could cause. You know, if in fact they could bring down other satellites. Is there a uniform convention that has removed this from attorneys suing on for damages between countries' satellites, for example? You know, we see all these ads on TV, have you been injured? And the legal profession is handing out lots of money in liability suits, and I just wonder, has there been a convention through the UN or something to distinguish them to be no-fault insurance or something like that?
So my statement there is that we don't need these guys going to space and doing anything in space. But the bottom line is that it would be difficult to do that because the paint chip, you can no longer identify who owns the paint chip.
Yeah.
And so you run into that issue there that becomes a problem. And the other part of that is that, you know, once you're in space, it's more the UN that deals with the issues rather than the individual countries.
Thank you.
Yeah, and I think if you're interested, Richard, too, in that topic, we do have a presenter a couple of weeks from now, Franz van der Donk from the University of Nebraska, Lincoln. He's actually a PhD. I believe he's an attorney, but he is the Othmer Chair of Space Law. So he's going to be talking about just, you know, legal parameters for the operation of communication satellites. So that might help address some of what is being considered from a legal standpoint. So tune into that one, please. And Julianne, are there any questions out in the Oak Room audience?
Any questions here?
I have a few more if there aren't.
Go ahead, Paula.
Okay, so I guess just maybe some basic questions on, you know, at the beginning of your talk, you were discussing that satellite operators get warnings. And, you know, I was curious how those warnings are provided and specifically how all of this debris is tracked and who tracks it.
So the debris is being tracked by the U.S. military. They are to the point that they will provide the information to us, but they're trying to get out of that business because there are just too many operators now and too many satellites now. So they're offloading those things. So there are different companies now that are going in. So Celestrak is one of those. STK is another. There are lots of companies that are getting into it. No one has a full-fledged program in place yet. So that's why the Space Force is still doing it, but they're backing away from doing it on a regular basis. Okay. Now, once you launch a satellite, you are a registered operator. And so if something is coming in close proximity to your satellite, in close proximity, we're talking multiple kilometers here, okay? But if something is coming in close proximity to your satellite, what will happen is that you will get a notice from them. So I get notices on our DebriSat, not DebriSat, our SwampSat satellite that is, in proximity of something else. Unfortunately, we have no power on board, so we can't do any maneuvers, okay? So the other operators would have to deal with that. But you do get, as an operator, you do get that information. And to go to space, you have to be registered as an operator. So that information is provided to you.
Okay. All right, thank you. I see a hand up, Bill Rossi.
Yes. I may have forgotten some of my physics, but it seems to me that at close-in space, at a given orbit, all things should be traveling at the same velocity. Is that not correct?
State that again.
At a given orbit, everything in that orbit should be traveling at the same speed.
Depends on where you are in the orbit. So if my orbit is elliptical, when I'm at the periaps, I'm going very fast. When I'm at the apoaps, I'm going very slow. So the speed is a function of the shape of the orbit.
Yes, for any given thing. But everything in that orbit, wouldn't it be traveling at the same relative speed?
Again, the speed is a function of where you are in the orbit. If the orbit is circular, by the way, there are no truly circular orbits, because circular means that I have an eccentricity of exactly 0, and I can't have that. Okay, so you'll have really small elliptic orbits. But if I'm in a really small elliptic orbit, almost circular, call it circular, then everything on that orbit will have the same speed. If the eccentricity is greater than, say, 0.05 or even 0.02, there is a difference between the periap speed and the apoap speed, and all points along the orbit, the speed changes.
And that's how these collisions occur then?
The collisions occur for several reasons. They're also in different planes. So if you think about the Earth, think about a baseball or a basketball in your hand. If you go straight across horizontally, that's your equatorial plane. And if you go at any inclinations from that, you can go from 0 up to 90, and then you can go back over to 180. So you can have prograde orbits, which is 0 to 90, and then you have retrograde orbits. The bottom line is that the Russian satellites typically congregate close to 60 plus degrees. So you'll have them in 66, 65, thereabouts. And the US satellites typically cluster either around 28.5 degrees from the East Coast, or they're in sun synchronous orbits, which are orbits close to 90 degrees, which are launched from the West Coast. And so you get those sorts of things. And because of that distribution is why you have the likelihood of collisions.
I see. Thank you.
Paul, go ahead.
Okay, thank you so much. I probably know enough to be very dangerous now, but I am wondering whether there is a point, or do you think there is a point, and is it nearby, when there'll be so much debris in space that we have to either curtail or actually stop because of the risk sending satellites or people to space?
Well, it depends on who you talk to at the moment. There is a group of folks, I made mention of Kessler earlier. There's a group of folks who believe we're close to that Kessler point where a collision will sustain multiple collisions afterwards because the debris is so much. And there are those who also of the field that we're not close to that point yet, and that the Kessler syndrome is a facade. The bottom line is, I believe the Kessler syndrome is for real. I don't believe that we're critically at that point, but if we start to look at removing things now, we will never get to that point. And so we will never get to the point of proving whether Kessler is right or wrong. I don't think we want to do that. So if we start now and start removing things now, we will be in a better position later on. And so that's why now the regulation says, once you launch something now, you have to have mechanisms, stated mechanisms of when you expect it to come back down and how it will be removed.
Thank you.
And I had another question. So given the huge amount of debris that is generated by these ASAT activities, you know, from an international standpoint, I'm curious why we're allowing that activity. And maybe that's something that, you know, is going to be in that realm of, you know, SATCOM law. And we're, you know, we're a little behind the curve on regulations, but I was wondering what your thoughts were on where we're headed with that.
So the issue with that is the US can make laws that nobody from the US can do an ASAT mission, although we have done that in the past, right? The US cannot tell Canada, for example, or Mexico, or anyone else that they can't have an ASAT mission. And so the issue right now is that the behaviors are solely associated with the countries of origins, okay? So US and Russia were the first to do ASAT missions. Russia was actually the first. And then we demonstrated afterwards that we could do it, simply to show that we are as powerful as they are, okay? Then China came along and did theirs, and then you had India that came along and did theirs in 19. The issue is we can't stop India from doing another one. We can't stop China from doing another one. There just aren't any laws that we can go to say you are not allowed to do that. Now, if they were to shoot down one of your satellites, that would be different. But they could shoot down one of their own.
Yeah, I was just wondering if there was, you know, a move afoot collectively from a global perspective, so amongst countries to start addressing this, you know, rather than
yes. The short answer is yes. The long answer is that, you know, you're talking about countries. You're talking about US and Russia and China as dominant people in this field. We're sitting in a room, who's going to listen to the other person? And what rules do the US have to impose on China? What rules does China have to impose on the US? And that's where we are in this discussion. Having said that, however, the operators are much more responsive than the individual countries, I would believe.
Okay, very good. Well, unless there are any other questions, Julianne, are there any hands up your way?
I don't think so.
Okay, well, I want to thank you very much, Dr. Fitz-Coy. That was a really fascinating talk. I, for one, learned a lot, and I'm hoping we're going to be blowing up less things in space and working more toward getting rid of what's out there that needs to come down. So keep up the good work, and thank you again for your time. I'd also like to remind everybody that next week we're going to be talking about plants in space. So how we're going to get plants to adapt and thrive in microgravity so that we can take them with us as we travel into space. So hopefully everybody will tune in next week. And thank you again to Dr. Fitz-Coy.
Thank you all.
Thank you. Stay well, everyone.